Welcome all. Mark and I are back on a new platform. This platform now allows us to have more of you join us during these online training sessions. And thank you for logging in today. The topic that we have up for discussion is troubleshooting the fault code F8. So over the next hour and a bit, I think we've added a little bit to this presentation from the previous one. Mark and I will be reviewing some of the methods of approaching and correcting this fault that you may come across in the field. This information in this presentation is based on real-world problem solving. So these have been things that we've used in tech support, on job site visits, etc., and just been basically logging this information and kind of compiling this information so that we can share it with you. And hopefully some of these techniques will help you work through one of these F8 faults. It's not reasonable to think that we can cover 100% of the possible issues that would cause an F8 fault out there. As you're going to see, there are quite a few variables and external influences to consider when you are troubleshooting any fault really, but in particular with the F8 faults, as you're going to see. But I'm pretty confident with this information and this documentation that we're having and providing you that it's going to really help you, or at least direct you towards the how to resolve this issue if you come across it out there in the field. The objective of the presentations that Mark and I put together here and we present live is to create a library for you of information that you can use as a supplement with the product documentation. And that information now will be archived and will be available essentially when you need it, when you have this fault and you're working through it. So before we get going into the troubleshooting, I just want to introduce and say hi to Mark out there. We're basically in separate offices, but virtually we're side by side. So hello, Mark.
Thanks, Scott. Just a couple of housekeeping things on my end. You'll see a question box that you can ask questions. I will monitor that while Scott's talking, and I will try to answer in real time those questions. If there's ones that we need to kind of hang on to the end, or if we have more than the time allot, we'll hang on at the end and we'll try to answer them verbally. But I'm going to type the questions or the answers to your questions in, and then everybody should be able to see the answer to that. I think you can ask the question privately. So if you want something that you only want me to answer to you, please make sure that's noted in the question, and I'll just send it to you directly rather than the group. But I think for most cases, if you have a question, everybody has the same question. So feel free to ask the questions, and we'll try to go through those as we go. And I'm going to turn it back to Scott. Let him yatter on for a while, because it's nice when somebody else talks per day.
There you go. That's right. And with all this extra room we have in here now, we can actually have a lot more room to breathe doing this presentation. So virtually, I guess. So thanks, Mark, for that. So Mark's going to be basically at the controls and making sure that your questions are answered, etc. As I mentioned, I think we're going to be a little bit over an hour here. Not too much. It just depends again on some questions at the end. But if you can't hang on for the full time that we're doing the presentation, again, get those questions in. We'll get the answer to you, whether it's via email or some other method there. So again, it's a fault code F8 that we're troubleshooting, and that's specific to a couple of different products that we sell. So I think it's prudent that we first start off with just a quick review of those particular boilers and controls that you'll see this fault on. So first off, the oldest of the boilers that you might see the F8 fault will be the CM2. So commercial boilers, you can see here from inputs as low as 133,000 BTUs. We're going all the ways up to about 2.245 million BTUs with these boilers. The first three, the CM2 186, 246, and 311, are the oldest of the boilers here. They were manufactured, and we were selling these probably a year or so before the larger boilers came out to market. These units are all the same footprint. So if you are coming across a CM2 186 or a CM2 311, you really wouldn't know which boiler you were working on there unless you physically looked at the model number on the sticker on the top of the boiler. Or there's some differences in the burners. And of course, when you open up the boiler door and look inside of the boiler, you're going to see the heat exchanger. There's flue gas passageways that are a bit different between the boilers. Obviously, for bigger volumes of flue gas, we need to have a few more slots for the bigger ones. But as far as a footprint, that unit is basically the same between the 186 and the 311 dimensionally. The CM2 400, 500, 620 are not the same footprint. There are different footprints there, but there is some identity here I wanted to kind of point out to you to identify which units you're kind of standing in front of. If it's a single door, so you can see on the left-hand side of the screen that you guys are looking at, with just the one on it, that's the CM2 186, 246, or 311. So the smaller boilers are on the left-hand side of the screen, and a single door on that particular boiler. And of course, on the right-hand side, you see that the 400 to the 620 has two doors. Why would I point that out other than the differences between the two here? That also identifies that the units had a bit of a different installation requirement. The CM2 186 to 311 would be installed a bit differently as far as assembling the components of the boiler on site than the 400 to 620. And that might be one of the reasons why the F8 fault is occurring on your boiler. So I just want to kind of mention that at the beginning with these particular units, that there is a difference between the doors, but also kind of a mind's eye there that there's a difference between how these boilers should have been installed or assembled in the field. These units also use a similar control in the GW6B, we call this unit. It is programmable for three different types of controllability. So you have, if you had a single CM2 boiler in a mechanical room, you could program this as a standalone boiler control, and it would have the ability of wiring an outdoor sensor to it, and domestic hot water sensors and supply temperature sensors. So it would be basically a boiler plant in a single boiler application. You also have the ability of programming in a multiple boiler system, where if you had two or more CM2s in a boiler room, we could take one control, and you can see this is actually a display you see on the top of the screen here on this slide. This control is programmed for a cascade, so it will control multiple boilers, but it'll also control the burner on that main boiler it's on. So we call it a cascade lead control when it's programmed like this. You would also have the other boilers that are in that sequence now that are attached to this main cascade control. We can program those as lag boiler control. So you can have up to one cascade control and 7 lag boiler controls. So 8 boilers in a boiler package here. If you did the math on that with the CM2 620, you're up around, I think it's around 19 million BTUs or so of input with that particular unit, all the way down to 450,000 BTUs up to that 19 billion. So it gives you a pretty good range as far as your BTU input. Also, kind of something to mention here with these CM2s, I think they were first brought out around 2012 or 2013. It was the first premix burner that Viessmann had brought over to North America on a high mass commercial boiler. And of course, we've got 8 years or so of experience now under our belt with these units. There's been a couple of changes on the burner side I want to point out to you. Some of those are directly related to solving issues with the fault F8. So that's going to come up a little bit later on in the presentation. So that's the CM2 boilers, boiler line. So 6 boilers there. You'll see those in standalone applications. You'll see them in multiple boiler applications. You may even see these in common vented applications. So we could have up to 4 boilers on one single vent. So there's some real flexibility as far as this particular unit and installation in the field as you require it. The other unit that we will look at today that is related to or could be influenced by the fault F8 is going to be the CA3B boiler. And you see that in front of you here now on the slide. This unit is Viessmann's newest commercial boiler. So we brought this out, I think, about 2016, 2017. So it's been out there for a few years now. And it's actually 12 boilers. So you see 6 in front of you here, from the CA3B 2.5 always up to the CA3B 6.0. But that is in a single fuel as well as a dual fuel application. So when you are ordering this and you have a single fuel application, whether it's natural gas or propane, you would order that single fuel boiler and one of the inputs that you see here in front of you. If you have a dual fuel application, so you need to switch between natural gas and propane in the field, you would buy the dual fuel boiler, and that would allow you to basically, as a contractor, to switch between fuels by just turning this keyed switch that you see there. I just popped up on the screen. So as simple as just turning the switch, we will now change from natural gas to propane, and switch it back, you'll go right back to natural gas. So it is a pretty unique boiler in that respect. Of course, both of those fuels are set up at commissioning to make sure that when you turn that switch that we're in proper inputs and your flame characteristics are all good to go, etc. These units, as you see, are multiple burner. It's a little cutaway there on the right-hand side of the screen. You'll see multiple burners, multiple pressure vessels in these boilers, but one vent out the back. You can't quite see that, but that's in the back there. So these units are always common vented. So with multiple burners and multiple pressure vessels, you could have one burner firing when the other ones are off. And there's, of course, there's going to be some built-in safeties in there, interlocks, to make sure all that is going to happen safely. But we are common venting these boilers right out of the box here. It's also possible to put up to four CA3 boilers on a single vent. So you can have, 4 6 million BTU CA3Bs and have one single vent to vent those boilers out. They use a similar control, a GW6C we call it, as what we just saw on the CM2. And there are some differences between these controls because we're dealing with a multiple burner and multiple pressure vessel boiler here in the CA3B. There's different interlocks, as I just mentioned. It's a common vented unit all the time. So there's different interlocks that are going to be on the GW6C that wouldn't be on the GW6B. So they do operate a little bit differently between the two units. However, as far as the fault F8 goes, everything that we do here is going to be the same. So how we would navigate through all that will be the same between these two units as we move through. So there's not really a big difference on that side. So you see the numbers here. You could have 2 burners up to 3 burners on a single CA3. So it just depends on the size that you're looking at there. Okay. The control that you see in front of you here now. So we just reviewed the boiler controls. Those are the GW6B and the GW6C, depending on the burner that you're looking at. The burner control that we have in front of you here will be on the burners on the CM2 as well as the the CA3B burners. This is the burner control. And when you have the fault F8, this is where you're going to see that fault appear. You'll see F8 on the display here, flashing to let you know that the burner control has locked out the burner. And the reason why you've locked out the burner, as we see here in the, this was just basically a cut and pasted right from the manuals for the CM2 and the CA3B. The F8 fault will extinguish the flame extinguished during operation is the reason why the F8 fault has appeared on your control. So the flame was there, we had a flame, it sensed it, and then it disappeared, sheared off, became unstable, something happened and it dropped out. Or according to the flame rod in the boiler ionization electrode, the flame was extinguished. And there's a couple of reasons for that. If you look at the information in the middle there, and then of course, on the right-hand side of the troubleshooting, it tells you the course of action, what we're going to look at here. So we're going to review a few of these things, but as you go through that, you can kind of get an idea that it's an ignition fault, right? So it's all related to, the burner tube, burner gauze assembly, combustion characteristics, incorrect fuel type, being selected. So everything in there has to do with the fuel, air, and ignition, and something going on there that the control didn't like, and that's why you're getting the F8 fault. So without this information, obviously very difficult to troubleshoot. If you're standing in front of a boiler and of course you see any fault on a control and you don't have a manual or information on it, it's very difficult to know how to get to the destination of actually fixing that problem. You don't have a roadmap to figure out where you need to go to get that, to basically solve that problem. Manuals are available. Of course, they came with the boilers. Sometimes they're not available. They're in a different area or they are not with the boiler. But if you go to our website, so in Canada here, we have Viessmann.ca and a Pro Toolbox area. And you can go on here and you can get the manuals that you're looking for. Anything current or anything past and documentation will be available in a PDF form here. So you can always, and it's always updated, so you get the most updated documentation available. Also, we have the Viessmann Orange app. So there's a little link on the screen there to basically get this loaded onto your tablet or your phone, whatever it is that you have that you'll use in the field there as far as helping you troubleshoot to get this information. And if you get this on your device, now you have a direct link to all these manuals and documentation. There's a fault code checker that's available when you have this, whether you go on the website or you have the app on your phone. You will get a fault code checker there, and you just type that fault in and it's going to pop up with the information and then also a direct link to the manual to help you troubleshoot. So there's lots of good resources that are available to you that will help you and assist you even if you don't have that manual on site. So just like this presentation, hopefully will be a good resource for you. These bits of information are available 24 hours a day, 7 days a week, 365 days a year, as long as you have access to the internet and you got a good Wi-Fi connection, you can load the stuff onto your device. So there's the F8 fault. Yep.
Sorry, Scott, just to interrupt you for a sec.
Yep.
When you go to the website of the Pro Toolbox or you get the V Orange app, both of those you'll be able to access those from your phone. If you don't know how to get to them, if you go to the Viessmann North America YouTube channel, there are some short 3, 4, 5 minute videos on how to use how to get the V Orange app, how to get to the different toolboxes, how to use the fault code checker. So that we've started to put up a whole bunch of just short little training videos that you can get to. So you know, if you're trying to figure out, can't remember what Scott said, go to the YouTube channel, look for Viessmann Orange app or Pro Toolbox and stuff like that, and see what videos are up there to help you out.
Excellent. Yeah, and like I say, this video or this presentation will be part of that archive there as well eventually, but lots of good resources there. Thanks, Mark, for pointing that out. Once we have the idea of the fault, so that F8 fault that we're working on there, it's important to know when that will occur on your boiler. So as we're hit the reset button and the boiler's firing up, if you're looking at that combustion control we just had a look at there, the burner control, it's going to go through a bunch of startup phases. So different phases as it moves through, and just like any type of combustion controller, it's checking for different safeties to make sure that gas valve opened correctly or the fan speed is correct, all those types of things. So it's doing a bunch of different tests of the components on the burner to make sure that it passes the test. And if it proves that those components are operating effectively, it'll just move on to the next phase. So it does everything from adjusting and checking the different pressure switches on the burner control, fan speeds, all those things are checked. When we get to the ignition time, so right at phase 4, you see on the screen there's pre-ignition. There's going to be some things that are going to happen to the burner control, depending on the size of the burner we're dealing with. And then it's going to trial for ignition. So you got phase 5, and that's the point where the flame is detected on phase 5. So we know that we get past phase 5 when we get the F8 fault, because it says that the flame was extinguished, so it knew there was a flame there. But at phase 6, it needs to stabilize. So if that flame can't stabilize, that is when we end up with the F8 fault flashing on our control screen. So characteristics in the combustion area are not what the control would be looking for, and that's when that F8 fault is going to occur. So we're going to work through some of those things that might cause some instability in your flame during that stabilization period at phase 6. So that's the area that we're kind of focusing in on. If we can get past phase 6 and into 7, that is when the burner starts to modulate. So at that point, that's when we are out of the safety circuit, and now we're into control circuit of the burner to your to whatever set point the control has based on the load that you're dealing with at that point in time. I like to go through the simplest things first when you do these little exercises. So when you come into my classes here, when we, someday when we get back to live training again, and whatever that might look like. But usually we'll go through a service seminars and training, and I always start out with the easiest things first. But that's going to mean you're going to need to have specific components. We're talking about commercial boilers here, so I think the guys that are listening in here are all loaded up and ready to go as far as the tools of the trade here. But the first thing you would want to check on any F8 fault is what is the gas pressure. All right. So here it says in here model 186 to 620. You'll see on here, but it's actually the same for all the burners, whether it's a CM2 or a Vitocrossal 300 CA3B. These gas pressures are all the same. If you were to check your static pressure, we don't want to see anything higher than 14 inches. And you'll see right in the middle of the screen there, the little test port is right below the gas valve. So that spot where we want you to check your pressure here and make sure it's not over 14 inches would be right at this spot, just below the entrance into the gas valve. This little flange adapter that's part of the gas valve connection, installation. A little set screw is in there, a little flathead. You back that set screw out a turn and a half, and put your manometer, your magnehelic gauge, whatever you're using to measure that pressure there, turn the gas on, and it needs to level off under or at 14 inches for you to safely start that burner. If it's above 14 inches, that's probably a good reason why you're dealing with an F8 fault. Remember, instability in the flame, we got too much gas pressure based on burner tube surface area and volume. There could be some issue there on the ignition where we're going to get some resonance, and that's going to cause some instability. So we want to adjust that gas pressure down below that 14 inches. But when the burner, we also want to measure that when the burner is actually in operation. So static pressure is one area. We also want to let the boiler go through a trial for ignition here and have a look at what that pressure drop is. We see here on the screen, we can't drop below 4 inches of gas pressure on natural gas, and we have a little higher limit there of 10 inches for propane. So 14 to 10 inches on propane, 4 to 14 for natural gas. If there's some issue there where we have a wide differential in pressure, that could indicate some stuff in your gas piping. We've seen, shards of metal from stuck in the screen of the gas valve to insulation when the pipe was pulled through walls, that sort of thing. So if you're dealing with a high pressure drop, you might want to check that to make sure that there's nothing obstructing the flow of gas into the gas valve at that particular point in time. But gas pressure is critical on any ignition fault, and no different here. We just want to make sure that that's set up correctly so we're not dealing with any issues on that particular side of the valve. The other area to look at related to gas pressure again here is sometimes it's beneficial to basically have basically a point where we can separate gas delivery from the actual ignition side of the boiler. And in some jurisdictions, these gas pressure switches are already part of your system. There is a low gas pressure switch on the gas valves that come with all the boilers that we're talking about here today. It's called GDW1 in the manuals. That's our low gas pressure switch. It's set for 4 inches on natural gas. So if the gas pressure is down below 4 inches, basically the burner is not allowed to fire. You end up with a kind of a wait state fault. But once the gas pressure is basically sensed by that pressure switch, it automatically resets and the burner would be allowed to fire. In some jurisdictions, that's not desirable. They want a manual lockout if the gas pressure drops, so that there could be some investigation as to why that dropped. And of course, somebody with the appropriate trade qualification has to go in and push that reset switch. On the high gas pressure side, this would be beneficial for the F8 fault in particular, and obviously low pressure. If we were dealing with high lockup pressures, you're dealing with some pretty good sized appliance regs when you're dealing with some of these boilers. And depending on the type of regulator, vented versus unvented regs, the proximity of that reg to the boiler, the pipe diameter sizes between the reg and downstream into the burner. You could be dealing with some high lockup pressures occasionally, depending on when that burner last fired and if that burner dropped out at a higher firing rate than it did previously. You could have a high lockup pressure there, and sometimes having the ability to just have that high gas pressure switch open would tell the gas fitter, the gas technician here, that the issue is basically upstream of the boiler. It's caused by a high lockup problem. So identifying that and basically making the appropriate repairs and fixes there will ensure that that lockup pressure doesn't go too high. And of course, we keep ourselves out of that F8 fault territory. So just like low pressure, obviously high lockup pressure can have an impact on your burner control and your operation. So there's a picture here of a gas pressure switch that would be typical that you would use, and basically very simple, pipe it in line with your gas piping before it connects to the burner. You just have a tee off here and put a gas pressure switch in there and interlock that. You see here the connections in the manual. We show the connections to interlock that device so that the burner is locked out as well if that gas pressure switch goes into the open position. So high gas pressure can be a cause of the F8 fault, and this would just basically give you that dividing line between it's a gas delivery issue versus F8 fault on the burner. We also have in some of the burners, not all of them, we have a rotary damper. And you can see at that phase 4, that damper closes and chokes off the air. And what that's meant to do is basically between 4 and 5 is the ignition. So we choke off the air during that ignition or trial for ignition, and that reduces the amount of air for the amount of gas that we're putting into the burner. So it gives us a nice soft light off. That's the intent of choking that air back. Different burners have different damper closure. So the 186 is not mentioned here. It doesn't use this rotary damper. It uses a choke that's connected to the gas valve to create basically an influence on the gas input when the burner goes to light off. These burners with the rotary dampers kind of do the similar thing. They just choke the air off versus adding a bit more gas on ignition. And you can see that 246 and 311, that damper basically chokes off to about the 35 degree mark before the burner goes to light off. So it's obviously important to make sure that that rotary damper is going to the right closure position, as well as the servo motor is working, that linkage is basically connected properly. There's nothing jammed up in the rotary damper here. Nothing's been sucked up on the combustion air side of the boiler and basically jamming up inside of that. So good to inspect the rotary dampers of your boilers as well. There's a shroud on the CM2 rotary dampers. There isn't one on the CA3B. So the CM2s, you have to take the little shroud off and have a look inside there to see if there's anything going on, which is connected directly to the combustion air pipe on the CM2 boilers. So that's again, the 186 has no damper. 246 and 311, this damper is related to, as well as the CA3Bs, the 400, the CM2 400 and 620. But the difference here is that we got a 30 degree close on the 400, and we're down to 20 degree close on the 620 on ignition. And then The CA3B has a damper as well. So the 2.5 to 3.0s don't have the rotary damper. The 3.5 to 6.0s have the rotary dampers. You can see the positions there as well. So just to investigate quickly what that looks like, how that operates during that phase 4 to 5 to make sure everything is good on that side and it's functioning correctly. If it isn't, we need to make sure that we repair that and get that in a good working state. Another area that we can look at with the combustion controller on both boilers, you can see here there is a menu level 5. So there is a service level that you can get into on the combustion controller. We're going to show you how to do that here in a minute. But in this particular menu level 5, it's meant to help you as a technician, and you're doing some troubleshooting, to basically have a look at monitoring some of those different components that are in the boiler. So we can have a look at everything from what the boiler temperature sensor is, your flue gas temperature you see there. You've got different speeds of the fan, where the gas pressure switches position, are they open or closed, air pressure switches, all those things. We can actually physically watch the control and what state those are in. The one I want to hone in on, and you probably noticed it because I skipped it, was the little information here at level 3. So sub-menu item 3 is your ionization current. And we can, without putting our microamp DC meter in series with the ionization rod, we can actually just watch this ionization current during the operation of the boiler. So it's available here. You'll see down at the bottom, and we give you some examples of how to access this. But Mark has done a very nice video here that actually shows you how to access, how to find this ionization current. So first thing Mark does is he puts his hand or finger on the S, holds it down, and you'll notice that above the wrench, a little flash, and he does it very fast here. He scrolls up to 5, hits the S button, scrolls up to 3, hits the S button again. That's his microamp DC signal at 14.6. And then to get out of it, he pushes the S again, holds it down until the little LED flashes above the wrench, scrolls up to 5, hits the S button twice. Now he's back into, you can see here, phase 7. So this burner is running. If we looked at, remember the sequence of operation I reviewed with you earlier, when you see 7 on that combustion controller, it's telling you that that burner is in modulation. Now, you could also do this particular exercise before the burner even goes to fire. So if we're looking at an F8 fault, we know that that is the flame was extinguished. So how does the control know the flame extinguished? It's based on the flame signal. So if we can have a look at the flame signal during the burner operation, that might give us a really good indication of what's happening in that combustion area. So what I propose to you is when you have the burner basically trialing for ignition, so it's starting up and it's going through its phases, do the exact same thing we just saw here. So hold the S button down until a little LED flashes above the wrench, and then use the up arrow key to go to 5. Hit the S button, then scroll to 3, hit the S button, and wait, sit there and wait and watch that screen on that combustion controller. When the burner hits that 4 and goes into pre-ignition and then 5 for ignition, you'll actually see that flame signal. And generally speaking, what you should see there, if everything's in a good combustion state, typically we would see at least a 3 microamp DC signal here, and it would climb fairly quickly from 3 on up. With the F8 fault, what you tend to see here is it might hit 3, maybe a little higher than 3, then it drops down into a little valley of flame signal. So it drops down. If it doesn't get up above that 3 again during that stabilization phase, that's generally when you're going to see that F8 fault lock out. So when we see a microamp signal down below 3, it's typically a good indication that we might have some issue on our electrodes and ignition side of the control. So the flame signal is not being measured correctly here. So what we want to do at that point, now that we know where to find that information on where that flame signal lives, we could start having a look at what influences that flame signal. So obviously the electrodes here need to be positioned correctly. We would look at that. These are a little older set, kind of did that on purpose. You can see these are the ignition electrodes on a 186 boiler. And I like to use a set of metric Allen keys. In our manuals, it kind of gives the positions there in metric. If somebody out there has the equivalents in imperial Allen keys or hex keys, they might want to shout that out there. So maybe Mark can post that for everybody. But basically, if you've got the millimeter Allen keys, I just use them and slide them. So you see in the picture here, there is a distance of about 8 millimeters plus or minus 1 millimeter. So basically, you go from between 7 and 9 millimeters. That ignition electrode has to be off the mesh. Using an 8 millimeter Allen key, I slide that between the electrode and the mesh. And if that slides through without any obstruction, but not too much of a gap there, it's a really good reference and quickly check that out to make sure it's in a good spot. Same with the distance between the electrodes themselves, and of course where the actual ignition point is. All those areas are basically, that's what you're kind of marking out here when you get these in the proper position, that spark is going to be in the right spot. Obviously critical to avoid an F8 fault is lighting off on the right spot. If your electrodes are drifting like you see here, we're going to talk about electrodes in a little bit and what their makeup is, but with the electrodes, a lot of times you'll see that kind of get that gray kind of dull look to them. They're starting to lose their conductivity. If I put a meter across these electrodes right now and was checking for continuity, I probably wouldn't get it because they've got a little bit of a layering of silicate on them. And as well, they're out of position here. So the light off might be a little off here, maybe delayed, etc. If I hit this with a torch and I could actually bend these back into the right spot versus if I grab my pair of pliers and try to bend these, I would probably break them because they get brittle over time as they're in operation and service. But if I hit them with a torch and make them glow a little bit there, I can bend them, they're a bit more pliable, get them in the right spot, and then I give them a good scoring, clean them up there, and to make sure they have good conductivity. And that will be, if your ignition electrodes are out of whack there, that might be the reason why you're sitting there troubleshooting an F8 fault. So make sure they're in the right spot. If you do that exercise of sanding them down and hitting them with a torch to put them in the correct spot, I would make a note to come back, before another season to replace those electrodes, just to make sure that they're not going to be a problem during the heating season of operation there. And of course, the other electrode would be the ionization electrode. So on the 186 to the 311, that's the picture you see here. It's a little bit of a different ionization electrode than the other boilers we're going to have a look at. Just one measurement, between 10 to 14 millimeters off of the burner mesh that electrode has to be. Obviously critical for flame signal that we're in the right spot here. So checking this one out is valuable. You'll also notice that it can get some silicate on it there, get that kind of gray, kind of pasty look to it. And we want to make sure that, of course, if it's a flame rod, that it's going to have good conductivity, because it's basically dealing with that flame signal rectification back to the burner control. So the more insulated it is, the lower the value of the flame signal. Of course, we start dropping down into that valley, and now we start dealing with lockouts on the F8. So we want to make sure that that's in good shape. Just a little note on this electrode. You see, it's kind of it's kind of a U shape to it. It's not, it's not a straight ionization electrode like you're probably used to seeing. So it has a bit of a different method as far as removal and installation. In order to take this particular electrode out, you need to back the door off. So basically open the door up. It's usually not a big deal when we're dealing with F8 faults. And this particular burner, pretty easy to take the burner out and remove it, because it's basically attached directly to the door. So we open the door up, have a look at that electrode. If we need to replace it, what we would have to do at that point is have a look at the sensor lead. So where the ionization sensor is connected, take the sensor lead off And that little, essentially the little nut there has a little hex on the end that you can get a wrench on. You back that little nut off, and there's a washer there. Be careful. You see it up. You'll see that in a minute. And once you get that nut off here in the washer, now on the other side of the door, you can pull the electrode towards you, and that will remove the electrode. And of course, the porcelain goes out the other direction, and then just reverse the installation to get the new electrode back into place. So we'll put that back into place there. There we go, removing it. The larger boiler, so this would be the 400 to 620 in the CM2s. The electrodes look similar as far as the ignition electrode did to the previous CM2, the smaller guys. But the flame sensor electrode is in a different spot, a little different look to it. So it's a little longer, more straight, more kind of more of a conventional type of ionization electrode. But we see that there, and of course those positions, and we're to measure those, our ignition electrodes here. So there's the ignition electrode and the ionization electrode measurements. And same thing applies to these electrodes that did on the smaller ones. We need to make sure they're in the right spot and that they're good and conductive. There has been a change. So this has been one of those areas I mentioned with Premix burners and being one of the first to bring them to North America here. Dealing with some differences in the way Premix burner that size kind of operates and functions. The electrodes have gone through a little bit of a change here. So the ionization electrode that we have currently is what we call a knife electrode. And we've had previous electrodes basically what we call an APM style electrode. So there was some ferritic metal in there, or some iron. There was some aluminum in there, some other stuff in the alloys that made up the main electrode. With the knife electrode, we've added this little area here at the top you can kind of see on this electrode. And it's a different alloy. It's called a Haynes 230 alloy. So it's made up of nickel, chromium, and some other alloys in there. The thing to kind of think about with these types of electrodes is those are not melted together or molten and connected. They're actually sintered. So they use a powder of a metal, and they use pressure and temperature basically to form these electrodes together. And the idea behind that is they're a bit more thermally stable. So basically, as far as flex and bending and stuff, we're trying to avoid that. They're also a little harder as far as oxidation. So there's a bit of insulative there. The Haynes 230 is a bit different conductivity and a little bit more resistant to oxidation than the APM electrode, the standard straighter piece of metal you see here. What this extra piece of Haynes 230 alloy is doing there is basically adding on to that flame sensing. So when that flame is in some level of turbulence, this is going to pick up that flame is still in good solid operation. So you're going to basically spend less time in those ionization valleys that you would with the APM electrode. So it's just basically one that's going to, these electrodes basically get us through those valleys and basically avoiding those nuisance lockouts on the F8 fault. So if you are doing a service on a CM2 boiler, the 400, 500, 620, and that ionization electrode is not this style, you want to order this style of electrode for the flame signaling. That may be the reason why you're sitting there dealing with the F8 fault to begin with. So that is something that's been out for a couple of years there now. But just to keep that information so you know informed, because some burners could have been in operation for a number of years without that electrode being replaced, and we want to make sure that you get the correct electrode in there for proper flame sensing. The 400 and 620 burners also, this comes back to what I mentioned earlier, the one door versus the two door boiler. So when you come into a job site, you see the CM2 400 to 620, it's the boiler with two doors on it, the bottom door and the top door that sits on that bottom door. They came shipped a bit differently than the smaller units. So the smaller units, when they were shipped to the job site, the burner door and the burner itself were already, or sorry, the boiler door and the burner itself were already integrated. They're already installed together and they're in a box. And the installer would take that burner door and burner out of that box and mount it onto the boiler. So really it wasn't much you would have to do as far as, you know, that burner integration or installation. It was part of the door already. With the larger boilers here, there is a difference. The boiler door is already part of the boiler itself. So now this unit would come and you'd have the door already shipped, mounted on the boiler or the pressure vessel itself. And the burner would be in a box. And you notice the burner here in the big picture, we have a plastic shroud around that, burner tube. So that stainless steel burner tube we have wrapped around there to protect it from getting any contamination on the surface of that burner mesh. So the idea is that when the contractor installer now gets these particular boilers on site, he's got to take that burner out and he's got to slide it into the boiler door. And the idea here is not to remove that shroud from the burner tube when you do that, or you might pick up some contamination of insulation that is basically packed around the burner door itself. So we want to avoid that. We want to keep that shroud on the burner to make sure that we don't pick up any of those fiber contaminations. Of course, what that's going to do is potentially cause some issues as far as the flame. So it might distort the flame. It would get some unevenness to the burner tube as far as that ignition process. So we want to keep it nice and clean. And so part of that would be, you know, with an F8 fault with these bigger boilers, opening it up and just making sure that it doesn't have any contamination visible as far as, you know, pieces of insulation, et cetera, stuck onto that particular tube mesh. There's also a technical service bulletin that is on our website as well, and this is added from the previous presentation we did in the F8. So this is a bit it's been there for a while, but I added it to this particular presentation. It talks about the F8 fault on the CM2 boilers and a cause of that F8 fault. So 3 of them we already talked about in the F8 fault. Combustion characteristics are not ideal. This one here, where we have the condensate on the flame sensing electrode. So how does condensate get on the flame sensing electrode? Have a look at that here. You can see just at the base of the electrode, fairly close to the porcelain, you'll see a little bit of corrosion build up on the end there. If you have an F8 fault and you open up the boiler or you remove the electrode and you notice that you've got this type of corrosion around the electrode itself, it points to an issue where there was basically some insulation that may not have been installed in the burner door, or it may not have been applied correctly. So what we're looking at here is on site, and this is different from the smaller CM2s to the bigger ones. When that door, basically when that burner was slid through the door, that was step 1. The next step would have been to take some soft refractory material that came with the boiler and pack it around the burner door and the burner tube. So that whole, basically the distance between those two allows air basically across the burner door. It's not insulated to that particular spot, and you could get condensate forming on the burner door based on the temperature of the boiler room, of course, and the temperature inside the combustion zone here. So you could get condensate forming, and of course those that condensate forms, it would start to drop and run down the burner tube, and of course it drips right on that ionization electrode, creating that little bit of corrosion that you see on the electrode we saw there previously. So the idea here, you see that the refractory is packed in there, and the idea is to pack that in nice and tightly around that area. It's a soft refractory, so it's not rigid, but to make sure that that soft packed insulation doesn't extend past the porcelains of the electrodes. It's kind of the rule of thumb there. So just pack that in nice and tight. That ensures that the door is now completely insulated and that condensate's not going to form and then basically drip on your electrode and create that F8 fault. So something that could be dated back to the original installation here would need to be investigated to make sure that's not an issue. But you certainly see the signs of it and indications of it if you look at the ionization electrode when you're doing your troubleshooting. The CA3B is a bit of a different unit here. So instead of having a electrode block and an ionization block, it is basically a single block. So you buy the ionization and ignition electrodes as one piece here, and they're installed as a block, as you see here. And the distances between the different components are shown there on the left-hand side, where we need to be as far as the electrodes are all the same for the different CA3Bs, as far as the gap distances, et cetera, that we want to check out. This has also gone through that change as well. So we've added that knife ionization, so that Haynes 230 alloy is added to the ionization electrode on these particular boilers as well. And again, if you're dealing with some nuisance F8 faults and you take the electrode out and you don't have the knife electrode, you want to basically your first step would be to buy or order that 7858519, and that's going to be the proper electrode for your CA3Bs to make sure that if it's an ionization valley issue, this is going to basically help get us past that particular point of the ignition. So just replace the electrodes could be enough to solve the F8 fault. All right, so that's what it looks like. Again, a little bit closer up. We see it there. And of course, one of the other areas that was mentioned was combustion characteristics were not ideal. And that is basically, you can either go back to the combustion test report. So all the boilers that we're looking at here, this is a CA3B, for instance. When we do a combustion test report on that, there are specific steps with a CA3B. Each burner is tested separately, which means the other burners are in the off position, so they don't fire while you're setting up one burner. You leave one off, and then once that one's set up, you go to the next burner and leave that, and sequentially turn the burners off to make sure that there's no influence there. And you see that we do a reading on all boilers, not just the CA3B, CM2s as well. With premix burners, generally we do a test on high fire and a test on low fire. So we adjust our combustion numbers for a high fire setting, and then we adjust them for low fire. And never a bad idea, you know, it was pretty good to ramp back up again to high fire, and just to make sure if you made any adjustments on low fire, there's no influence there, because there are a couple of areas, we'll show you here how to set the burners up on the gas valve side here in a minute. But you see the test port is in the back of the CA3B. You back the little screw out, that blocks that area, and you put your combustion analyzer in there and do your combustion test report. So these are usually either kept on file or they're in the boiler room there somewhere, but really good information on the startup of the boilers could become critical as we go down the road. There's some really good information that is basically put on that combustion test report that could really help you down the road when you're doing your troubleshooting, if there's any characteristics here that have changed. We'll look at that in a second as we move
Just something
through
to point out here, Scott, while you're talking about combustion on the CA3s.
Sure.
The CA3 has more than one burner. It either has 2 or 3 burners.
Yes.
So when you do a combustion analysis, you need to put the other burners into standby so they don't run, because you only want to do a test on one burner at a time. So you don't ever want to have 2 burners running when you're doing a combustion test, because if there's something wrong with one, you won't be able to tell that. So one at a time. You'll be doing a lot of adjustments. Yeah, one at a time when you're doing it. So you can do that by putting the GW6 controls for the other burners into the standby, and then put the one you want to test in an emissions test mode.
And ramp through it. So we're going to show you how to do that here in just a second as we go through here. So there's your test port for the CA3s. And of course, on the CM2 units, there's showing here using a PPS vent. This is in our lab here in Langley. And we just have our little test port plug on the PPS venting, and that's where we take our flue gas measurement there as well. And you mentioned basically in this one here, combustion not properly set up for conditions, too much excess air is kind of the statement here. I put this one in. And what I find usually with an F8 fault is when you have that ignition, sometimes you're going to get a lot of movement in the combustion air ducting. That's like a real kind of pulsation going on there. That can be caused by a couple things, but sometimes that could be a result of a lot of excess air during operation. So when we fire that burner up and you start doing combustion tests on it, generally what I like to see as far as numbers there is if you can get your excess air down below the 30% range, if you're dealing with F8 faults, that goes a long ways for that a bit more smooth light off on ignition. So what I usually try to dial in is keep it above 25%. Premix burners, generally speaking, will operate down below 25%. But what happens is you're getting that flame really close to the burner tube itself. So you might start dealing with some issues as far as part replacements and component replacements because the flame is burning too close to the actual burner cylinder itself, and that would start to deform it and cause some issues. So generally above 25% excess air, by keeping that 25 to 30%, which gives you a good range for low fire to high fire. Generally, you want to have a bit more excess air on low fire and a little less on high fire. So I try to get a little bit closer to 25% on high fire and a little closer to 30 on low fire. But if you can keep within that range, what I find is a lot of times that would solve issues with intermittent F8 faults. Sometimes the temperature outside, we create some issues on the draft side that might be problematic intermittently, and you get that F8 fault. So this one here, like I say, just kind of having a look at those numbers goes a long way to kind of solving those kind of nuisance intermittent ones that you're dealing with sometimes. There might be some other things we're going to look at here as well on that pulsation on the combustion air duct we're going to talk about, but certainly excess air at a high number would be one there that we want to look at. So this is what Mark was talking about just a few minutes ago. How do we get into that combustion testing? The easiest way to do it, I mean, there's a couple ways you can kind of get around this, but this is kind of the standard procedure. It gives you better, I think, in my personal opinion, the best control of and information as you're doing your combustion startup. There's a little emission test switch you see on the top right hand on the screen there, and you see the little chimney sweep hat and ladder. There's a history behind that little symbol. Someday when you come to class, we can talk about it. When you push that down to the chimney sweep ladder, it's basically like an override button. So what we're doing there is when you push that to that position is the burner is going to fire to its limit. Just going to bounce off for its electronic or operating limit as far as operation. That's a really good way of doing a combustion test. We don't have to simulate a load. We just hit this switch and turn it on. So the burner is going to go through its phases. It's going to light off. Once the burner goes into ignition, we can actually take control of the burner modulation. If you hold the down arrow key and that S button down for a couple of seconds, what's going to happen is the screen will change, and you'll see now that P for basically firing position and whatever number in the modulation percentage that particular burner is at. So if you waited for a while on heat emission test switch and then you did this, you'd probably be at 100% of your input. So it'd be if you saw 100 there, that means the fan is at 100% of its fan speed and you're basically at the high fire position. Like to give the burner usually a few seconds of operation. You never want to throw your combustion analyzer in a pre-mixed burner system right after ignition, because like as I mentioned, a lot of times we're dealing with that nice golden light off on ignition, which usually means that we're fuel rich, which means your carbon monoxide numbers might be a little high, and of course we don't want to, it's pretty expensive to get those analyzers recalibrated and get new CO sensors in there or stuff like that. So if you hold off for 15-30 seconds or so, put your analyzer in there, usually it's enough that the numbers have settled up there, and you're not going to have any issues as far as alarms and stuff on your carbon monoxide. So we're going to adjust the boiler here on the emission test switch. The same thing here with the CA3B. When we're finished doing the emission test switch, all we do is put the emission test switch back to its default position. You see it on the bottom right of the screen there now. So put it back to the little tornado symbol, I call it, little basic automatic symbol. And on the control, we're going to hold those two buttons back down again to basically get out of the emission test switch. So once we finished setting up the burner, it's simply switch the emission test switch back to its normal position and hold those two buttons, S and the arrow button, down again, and the control will go back into automatic operation. So if it still needed to fire, it may still fire. You'll see basically 7 on the screen there telling you that it's in modulation mode at that particular point in time. So pretty straightforward. All the burners have this, and as Mark said, what you would do with the CA3Bs is you would put those other controls into standby while you're doing this to one of those particular burners, right? To make sure that we don't have the influence of another burner firing up. When we're making adjustments to our fuel-air ratio, we're kind of focusing in on the gas valve. So we're making a setup adjustments here for low fire and high fire on the 2 adjustments that you see here on the gas valve in front of you. So on the left-hand side is the high fire gas adjustment. You take that little that blue cap off of the gas valve, and in there is a little Allen keyed, I think it's like a 3 millimeter, 2.5 millimeter Allen keyed adjustment. So you're adjusting the valve there. And on the right-hand side is the low fire adjustment. So we've got the little offset for your zero governor gas valve here. You back off a little cap, and inside the little Torx adjustment screw there to make your adjustments. There are, basically when you do this, you're kind of going in 2 different areas. So if I want to increase CO2 on high fire, I'm going to take my Allen key that's basically attached to that to where that big blue cap was. I'm going to go counterclockwise. So when I go counterclockwise and I'm looking at my flue gas analyzer, I'm going to start to see the CO2 increase. If I'm in low fire position and I am in the zero governor offset there on the right-hand side with my Torx screw or Torx nut driver and turning that clockwise instead of counterclockwise, that's how I'd increase CO2 on low fire. So they're kind of opposite. If I go clockwise on the high fire adjustment, then I'm going to reduce CO2. If I go clockwise on the low fire adjustment, it's going to increase CO2. So they're kind of they're basically opposites attract there, or a little bit different. And why you're doing it, why they're different is, here's a picture of a gas valve that I've taken apart here just to kind of give you an idea. And the orange pen there basically points to the valve stem. This is the second valve stem. And when you are back in that counterclockwise, you are basically pulling that valve stem further away from the seat that the orange pen is pointing to inside the gas valve. So as I back that counterclockwise, I'm actually pulling that valve stem farther away from the seat position, allowing more gas to get in through the burner and then out to the burner tube, so increasing my CO2. So if I go the clockwise, of course, I'm closing that valve stem back towards the seat a little closer, which is going to reduce the amount of gas that's allowed to go through. On the zero governor side, on the offset here, when I go and push or go clockwise, you'll see I back the set screw completely out, and it's basically just attached to the spring that's inside of your diaphragm. So when I basically turn that, I increase the tension of that spring on the diaphragm, which basically closes off that zero governor adjustment. So there's less gas bypassing from the gas valve back into the diaphragm and closing off the amount of gas that's allowed to go into the burner. So as I increase that, essentially more gas is allowed to travel into the burner for combustion. If I go counterclockwise, that spring tension is reduced. And now as the burner operates, that spring now gets pressure on it. There's going to be gas that's going to be allowed to bypass down through the valve and up into the diaphragm, basically to close that valve stem off a little bit more on the gas valve itself. So that's why they're a little bit opposite as far as their operation on that side. So here's the first idea there. So we're looking at the combustion numbers that we want to see. We're going to be looking at here on a high fire. So again, if you need to increase the modulation, so once we've done that, hold the S and the down arrow key, we've hit the override switch.
and we want to ramp between low and high fire. If I hit the up arrow key, you see that little arrow kind of indicating that up arrow key. Hold that down to make sure that that P is at 100. So when it's at 100, I know that burner's at full out. I'm doing my combustion test here, and I'm focusing in on that little set screw that's connected to the valve stem, and I'm trying to dial in the numbers here that you see on the screen. So pretty much the same numbers, I think, on the CM2. So a natural gas, 8.5 to 9.5. Again, I like to see them closer to the 9s than the 8s there, excess air being what we're dealing with, depending on your application, influences of things like your combustion air duct runs, your vent runs, et cetera. All that stuff could change. But generally speaking, trying to get that closer to the 9.5 area here on natural gas, and this same with on the propane side, keeping that excess air to that limit. And so making that adjustment and do very subtle turns here, because it's really based on the pump on your combustion analyzer, how quick that your reaction time on your analyzer to a change is based on just how quick that pump on your combustion analyzer is actually working. So you might want to wait a few seconds, make a small adjustment here, like just incremental adjustments if you're really close, and just watch the combustion numbers here. And generally speaking, not uncommon high fire. Your CO is well below 50 parts per million, usually in the single digits sometimes here, and your excess air is in that 25 to 28% range, and your numbers all will fall into place here pretty nicely. So you'll have be able to set that up on this, and oftentimes because these boilers are all high mass, when you start them up, generally speaking, because we're dealing with low and high fire adjustments here, not a bunch of adjustments in between, your setup is, generally speaking, are usually fairly quick. Oftentimes you'll be able to set up that burner before that boiler actually trips on its operating limit, gets up to that maximum temperature. So make those adjustments. High mass boiler, you'll have some time there, even with a limit on your loads, to make those adjustments happen. And then when we go to the bigger boilers, so there's the 405 or 620, and it's kind of giving those numbers where your optimal numbers there between 8.7 and 10.5, and they're giving you those ranges, trying to kind of indicate where you want to dial it into. Again, all based on information in the lab, but in the real world there, you might have to make some other adjustments based on their conditions there. So just keep that excess air, as I mentioned, in mind. And the bigger boilers now, we're dealing with the CA3 B units. Again, the ranges are pretty close to the same here, 8.8 to 9.2. So generally speaking, your excess air on the CA3 boilers, because it's a different, the burner's mounted a bit differently, et cetera, and they're different types of pressure vessels. Your numbers there on excess air, generally speaking, I'm trying to get it up a little bit higher, usually about 28 to about 32% excess air is kind of the numbers I like to kind of dial these into to get good operation. So I set those up, and those are my ranges. And the gas valves I will mention that are on the burners have already been pre-adjusted for the burner size and for some characteristics of that particular boiler. So generally your setup is fairly limited. The control in the burner and the gas valve have already been kind of adjusted to operate. You're just kind of adjusting for kind of field conditions. If you were to replace a gas valve, very important to note that gas valve comes out of the box directly from Honeywell. And that's not set up at all for that particular burner. So there would be more adjustments for you to do there as far as setting that up. Just don't pop that gas valve on and turn it on and walk away. There would have to be some setup of that particular gas valve to make sure that it is set up per the particular boiler that you're working on there. And low fire, so once you get the high fire adjustment all set, we'll drop that unit down to low fire by pushing the down arrow key on the combustion controller. Basically down, you see here 0 on the screen, which is fine, but there's no change in the RPM of the fan from about 20 down to 0. So 20 is basically your low fire position. Down to 0 is still low fire position. So there's really no change there as far as operation. So wherever you want to go there, whatever you're comfortable with is fine, 0 or 20. And we'll make the exact same adjustments here according to the manual. So what are we looking at here? Between 8 and 9% CO2 on natural gas, up to about 9.5 to 10.5 on propane. And we're going to make adjustments here to increase. We're going to go clockwise, remember, right? To close off that bypass for zero governor. And so that allows more gas on that low fire position. And again, if you had to make some serious adjustments here, never a bad idea to toggle back up to high fire, because there is some influence, obviously, between both of these adjustment settings will influence combustion on low fire and high fire. Their influence is greater in this case on the low fire position. But if we're making large adjustments here, we want to go back just to make sure everything is good. And this is all part of the combustion test report, as I mentioned on the setup. So you can dial this in and basically put the cap back on. And once we get this guy set up, let's have a look at what the bigger boilers here, the 4 up to 620. You're at about 8.5% on CO2 plus 2%. So if we were going back to the previous numbers, you'll notice that CO2 is slightly lower on low fire than it is on high fire. So a little bit more excess air on that low fire position that we want to see on high fire. And then again, with the CA3B boilers, we're looking at that CO2 number is slightly lower in the low fire position for these particular burners as well. So always a good idea to have a little bit more excess air on high fire. Again, it's all about that flame and in the right position as far as stability and keeping that burner mesh in good condition. One of the other things that's come from tech support I wanted to mention here as well is which could cause some pulsation in your combustion air duct, for instance. Kind of what this talks about is some unfavorable resistance on the flue gas side of your boiler, which affects the combustion zone during the operation of the particular boiler. So that would be in particular long horizontal vent runs. So there's a big difference between horizontal vent runs and vertical vent runs. Vertical vent runs create some draft. So actually help and assist as far as, to a point on the stability inside the combustion area. Whereas a horizontal vent run basically creates resistance. So the longer that run, the more resistance, and of course, the more back pressure on ignition you're going to end up with during the operation. Or if you've got your venting, whatever was done, there's lots of 90 degree, especially back-to-back 90 degree elbows can create some issues there as well with vent resistance. If you have a long horizontal vent run and some sort of an issue with the pitch of the venting, and you start getting accumulation of condensate in your venting, and you get a reduction in the actual area that we have for venting as a result of that condensate, that can also cause some issues here. And what you usually end up with is during that operation, you'll get some resonance. You get some noise. In particular, you'll get that it's kind of like a surging in the combustion air duct, that little clear combustion air duct that's attached to the CM2 boilers in particular. You'll also hear it in the CA3Bs as well if there's some issue there. And the fix for that basically is this compensation tube that is connected to the venturi of the burners themselves. What's happening here is that when you have that surge, this is connected directly to that zero governor area of the gas valve. So basically on ignition, it creates an influence there which allows more gas to come into the burner during that particular operation. And if we have a surging in the vent, that influence there is not desirable. So we can remove that tube, compensating tube, from the burner and basically just connect the tube from the switch down to the gas valve itself, and eliminate the connection of this to the gas valve. And then start your burner up and make those adjustments on your CO2, because there will be some differences now because we don't have that influence of this the venturi pressure on our zero governor offset. So it require a little bit of an adjustment or setup of your burner again, just to make sure those numbers are in good operating condition. So this would be based on those characteristics we just talked about. So looking for long vent runs, horizontally, lots of 90s in your system, those types of things that will create a fairly good back pressure in the combustion zone. And that, of course, will create that instability in the flame, but also a negative influence on this compensating tube. So we'll remove that. All right, so that came from our technical support group network here in North America. And of course, I mentioned if you have F8 faults over time and you've got the combustion test report here, you'll see something in particular that we want to look at would be the combustion chamber pressure. If you've got a lot of fouling, so in new construction areas and boilers are being utilized to keep that building hot as the construction is going on, without a lot of attention being paid to the type of quality of the air that's moving through the boiler. Generally speaking, if you can write your name in the boiler after the installation, it's probably got a good degree of fouling on the inside of the boiler as well. We got to think that our boiler is like a vacuum cleaner, right? It basically, for every cubic foot of gas that burner is going to use, it's probably going to fire, maybe 25, or 30 cubic feet of air we require to operate that. So basically, about 13 cubic feet of air will be required for every cubic foot of gas. So that's a lot of air movement through the boiler. And if it is basically wasn't being protected, we've got contamination in our combustion area, in our combustion zone. And we can kind of point that out and have a look at the previous setup of a combustion chamber pressure, where that was sitting, and measure it. If you have a manometer here, we can have a look at that. And there is one particular switch you want to focus in on to have a look at that. But what will happen if we get contamination of combustion air is it actually gets into the burner tube. And if you get excessive fouling in the burner tube, of course, that's going to cause an instability in the flame on ignition, misfiring, delaying your ignition, and of course, the result might be that F8 fault. So a couple of things you can do here. Obviously, if you've got a lot of contamination that you can visibly see, then probably a good idea to clean that burner tube to begin with. You can take a check or compare the combustion pressure with what the setup was initially and what changes were apparent there. But if you need to clean the burner tube, regardless of if it's a CM2 or CA3, we need to remove the tube from the burner. And we can hit that with compressed air, so between about 130 and 150 pounds of compressed air to blow the air out of the burner mesh itself. In some cases, that may not even be enough with depending on the type of contamination that we're working with there. But generally speaking, I just kind of noted, let me go back a little bit. There is like a high fire type of combustion pressure we'll be looking at, somewhere around there. Low fire, so some information there. Those aren't written in stone. You take them as gospel because obviously your contaminated burner tube may cause some issues there. Your venting obviously would create some issues. If you have more fouling in the combustion chamber, those would be a little bit different. But just good general guidelines for you. These were taken from our boiler in the lab here from low to high fire. And of course, what we're trying to tee into here to see what that combustion chamber pressure is this air pressure switch 2, the little guy that's highlighted in green down below. We can take our manometer and tee it into that little hose that's connected from the air pressure switch to the burner door. And once we connect that there, I see I've got a little brass tee that I picked up. You can find those at different areas, hardware stores. And this one here, I think I got at a pet store for a water filter for a fish tank. But just something that will basically allow you to tee that in, put your manometer in there, and fire that burner. And if you're doing a setup, you need this to write down what your combustion chamber pressure is. If you're doing gas tests or troubleshooting tests, it's good to have this to set it up so you can measure these pressures as well. And that will give you a pretty good idea if you have the old combustion test report, if there is some changes there, right? If there is a reduction in that combustion chamber pressure, something going on there that a result of that burner tube being fouled up. So we've got that little T inserted there, and now we're basically measuring what that air pressure switch is measuring. Right. So, oh, sorry, this is the pressure. So there's a 0.22 at low fire and about 0.66 on high fire. So sorry about that. This is the test I did on the low fire and high fire adjustment. And to get the tube out of the different boilers, so with the Vitocrossal 300, the tube is actually separate from the actual burner chassis itself. When we remove the burner chassis, we'll have to remove a couple more bolts, and then we can actually take that burner tube right out. You can see one of our hand and arm models here doing a fine job taking that burner tube out. And now that you got that out, you can hit it with that 30 to 150 psi of air. The CM2 burners are a bit more integrated, so you can see there's a kind of an exploded diagram, and all of the bolts and stuff are actually connected at the burner door here. So we have to remove the fan, and then you can get access to the bolts that hold the burner cylinder together, and you can pull it out the opposite side to get access to that burner tube. And in some cases, if there's enough fouling in that burner tube, it may require you to wash it. And we're allowing basically get the okay to wash these burner tubes, but the recommendation is to ensure that it's thoroughly clean and dry before you reinstall it. So you can see the amount of debris that's coming out of these tubes in some areas. I got a couple more pictures of some tubes that we discovered. There's a bucket with a tube that looked like it was clean, but there's the amount of debris that came out of it. And you're probably going to wash it and then hit it with air anyway to dry it off. So it's always a good idea as a combination there. If you're going to wash that tube after the fact, still use compressed air, and basically that'll force a lot of that debris out that the washing doesn't quite get all of it, and also help to dry the mesh and stuff. So we're not installing in and firing a wet burner tube in the boiler. All right, so clean that up. We'll have a dramatic change in the amount of pressure that you see inside of the combustion zone, and that will create a more stable flame to work against any type of back pressure from the venting side of the boiler. Right, here's a nice picture of, on the left-hand side, you'll see that fouled up burner tube, and of course, after it's been cleaned and washed, the difference there where those little ports where that fuel and that air are moving out to fire, if they're blocked off, we're not getting a very good combustion at that particular point in time. So clean versus dirty, you can see the comparison here, nice up close and personal. And of course, if the reality is, the boiler itself, once it's on site there, if there is the possibility of contamination, we do have a template here available for a field supplied combustion air filter. So the specifics of the type of filter are detailed in here. I kind of detailed that and highlighted in red there. What type of filters you're going to use, the size of the filters, not to reduce them. Ultimately, if you're firing that boiler during any type of construction or any type of potential contamination, it's your responsibility to make sure that contamination doesn't get into the combustion zone. So make sure it's treated correctly, and that will ensure that once that burner is basically in operation, that we're going to have those F8 faults and issues, etc. That we're dealing with. So this is detailed in here. It's available if you need this information. Of course, it's available here on the presentation, but you can contact your local area rep and get this information into your hands. And on the combustion air side of the boiler, so we're looking at some other things that can cause the F8 fault. You'll see that combustion air duct. It's part of every CM2 boiler. So this is specific to the CM2 really because we have this, but because it's more of the ability to identify an issue. Just looking at that little translucent duct that you see there, that's not on the CA3. But we could have a similar impact in the CA3 as well if it's not identified. And that's either flue gas recirculation or negative pressure in a building can cause some issues and F8 faults on the units as well. So you see that combustion air duct, you see it kind of piped in and connected on the CM2 boilers, how nice and translucent that ducting is. In comparison to the one you see in the middle here, you can see that kind of got a yellowish kind of tinge to it. The fan on the right-hand side, you can see that corrosion on the aluminum housing of the fan, all related to flue gas getting into the combustion side of the boiler. And this is something that we need to avoid. So whether that is the combustion air being ducted too close to the exhaust vents that we're pulling that combustion, basically that flue gas back in for combustion again. We have to make some sort of changes there to make sure that we're not having a negative influence on our combustion air because it's being contaminated with the flue gas from the boiler. Or if there's a negative pressure in the building, something that's essentially causing that vent on the boiler now to become a ventilation duct for the building after the burner fires. So any type of residual flue gas that's in that vent is now going to be pulled back through the boiler, and of course it's going to come out the combustion air duct. But as it does that, you'll see the yellowing, and basically in some severe cases, the duct itself becomes completely opaque. You can't even see through it because it's so contaminated there. And of course, that's going to have a negative impact on a lot of components. You see the fan here. Fairly expensive piece of equipment here, slowly being deteriorated by a negative pressure in this instance. Obviously, electrodes are going to start to foul up. It'll foul up your burner tube, and those will cause the F8 fault to occur. So basically, having a look here at the symptoms of negative pressure, things like the combustion air duct, combustion air side of the boiler contamination, where you can see corrosion from that acidic condensate or flue gas getting back in the combustion side of the boiler, all are really good signs, and they need to basically be addressed. So if we don't address that particular issue, we just keep replacing the components, we'll never really solve that F8 fault until we actually get to the source of it, which is either negative pressure or flue gas recirculation. So we need to adjust and address for that. And of course, just boiler cleaning. So if there's some issue with things like, as a result of stuff like flue gas recirculation or negative pressure, that can really expedite or basically narrow the window between, servicing of the boiler. So if you've got an issue, pre-existing problem with flue gas recirculation, negative pressure, it's going to foul up your burners quicker. So that would mean more service. If you've got a lot of contamination from combustion air, that's going to require a service as well. Generally speaking, these are high mass boilers, or their flue gas passageways are fairly large in comparison to low mass boilers. Bigger amount of surface area to work with. So generally speaking, not too bad as far as the annual cleaning and maintenance, but it's important with the F8 fault to inspect to see if there's some sort of obstruction or issue there as far as the boiler cleaning. And there's no special tools we recommend for the boiler. Basically a good water jet, good spray of water, and hose the boiler down. In some cases, if there's flue gas recirculation, etc., you can use some citric acid. Those sort of materials, citric acid is good for getting out that brown kind of stain that you get from flue gas recirculation. So I'd recommend that. It's in our manuals, the types of materials that we'd recommend for service and cleaning. But you got to get that burner out, and this is a CA3B. You can see right down in there, and get into those. Get in, clean that surface out, flush the water through the gaps here. Take the P-trap out, make sure all the water flows down through a drain, and basically keep that heat exchanger in good working operation. The same with the CM2. Similar material as far as the stainless steel, different style of heat exchanger, a little different look to it, but the same thing applies as far as the cleaning. You can use things like citric acid. Anything safe for stainless steel as far as a cleaner would be okay. And we want to make sure we get those flue gas passageways nice and cleaned out. Just a water jet, basically, to flush those heat exchangers and get those surface areas nice and clean. And that will go a long ways to making sure that the stability in the combustion zone is maintained and basically avoiding those F8 faults as we operate. Well, that's all I have. That was it. I hope you found it informative. Like I say, there was a little bit. We actually did this presentation, I think, a month or so ago, but we added a few things to this one. Of course, this last little bit here is a video that Mark did again, firing a CM2 burner. You can kind of see that light off. It's kind of neat to watch. You can see how that burner lights and stuff like that in this. You got a couple nice angles of how this thing lights, so it's pretty neat to see. We are, I think, on again next week. Are we not, Mark, for another presentation?
Yes, we have another webinar next week.
Okay.
Online seminar.
Yes.
Apparently somebody owns the rights to the word webinar, so we have to be careful what we say now.
Yes. Web seminars.
It is going to be, let me see, EE and EB faults.
EE and EB, so that's the next one. So basically, if you are dealing with Vitocrossal 200 boilers, so this would be the low mass residential and commercial boilers, the EB and the EE fault would pertain to something I think you'd be interested in. So if you want to join us, that will be broadcasted out. You can certainly register for that. We'd be happy to have you. But do we have any questions?
We had 5 questions. We answered them all, so I think we're in good shape. One point on that video that Scott's shown you there is that we did that in the original lab at the Viessmann here in Waterloo, and it was a very small lab at that time. So that was a pretty warm little incident because my camera was only about 3 feet from that 2 million BTU boiler, so it was pretty nice and toasty. But you saw in the video, you can see that when the burner goes to high fire, the flame pattern isn't really that much bigger than it is in low fires, which is a nice thing about a premix burner. You don't need a monstrous combustion chamber for it. So there are lots of advantages to a premix burner, which is why we've kind of gone that direction for all of our condensing boilers.
Yeah, there's a number of things. Setting up is a lot easier than a diffusion style burner. Low fire, high fire adjustments, low NOx. So some environmental things are important there to deal with as well. But yeah, I find a pretty reliable burner as far as operation. We've been using them in low mass for years, and now I say that's since about 2012 the trend has been pre-mixed on the big commercial boilers as well. So if that's basically, if no other questions, I want to thank everybody for staying with us today, and like I say, I look forward to hopefully seeing you, or not seeing you, or basically having you join us again next week. We review the EB and the EE faults. So thanks very much.
Yeah, and there are other webinars or other online seminars happening too. So check your schedule. That the marketing departments of both the Can and the US. We've kind of joined together with the US on these. So they're going to be doing some that we haven't done, and we're doing some that they haven't done. So I don't know what the breakout here of who we had. So we maybe had some US participants and some Canadian participants, but we work as a team. The products in Canada and the US are the same. So they have the same technical specifications. The engineering is hubbed out of Waterloo here in Ontario, and then we kind of do for North American products. So if you want to join us again for one of the other ones, Scott and I have I think 2 more in before the middle of August, but I think there's a half a dozen or so in total. So make sure you pick up on the ones you want and sign up for those, and we'll see you again on the next time.
All right. Thanks, guys.